Hey everyone, so today we are going to talk about Gram Schmidt orthogonalization process, sometimes also called as Gram Schmidt orthonormalization process. I will come to it, but before this, please make sure you watch my earlier lecture where I have talked the motivation or the need that why one studies this process. Okay, so see that lecture, and today, since I have already talked about the motivation, I am not going to talk that again. So today we are going to actually see what the process is. Okay, so what is my V? V is my vector space over real numbers, or you can take complex numbers or rational numbers, but let me concentrate on real numbers. Okay, so V is my vector space over real numbers, and if I take a B, B is what? It is a subset of V. So let me call B as say V1, V2 up to Vn. So this B is a subset of the vector space V. The method says you can apply this method to any subset of a vector space. Once you apply Gram Schmidt process, you get a orthogonal set. So main aim of the process is to convert a given set into an orthogonal set. Okay, so here the vectors, this set need not be orthogonal. I have also talked about orthogonality in earlier lectures, link you can find in the description. But here when you say a set is orthogonal, when you take any two disjoint vectors, its inner product is 0. Okay, so my V is an inner product space, that means it's a vector space and some inner product is defined on V. So with respect to that inner product, if all the two distinct vectors has inner product 0, then we call such a set to be an orthogonal set. So what does this process do? It will convert any given set into an orthogonal set. So say U1, U2 up to Un. So this is also a subset of V. So if you want an orthogonal set, you take any subset of a vector space, you apply this process. Whatever the new set you get is the orthogonal set. Okay, and obviously these two sets will be different because here the vectors are not orthogonal, whereas here the vectors are orthogonal. So obviously the sets are different, but they are not that different. They are not that much different, as in what? When you take the subspace spanned by this set, the span of B, so we know that span of a subset is always a vector space or a subspace. I have proved earlier as well. You can see the link of the playlist. Okay. So what they proved is one can convert a non-orthogonal set into the orthogonal set. Moreover, this conversion happens very smoothly. Smoothly as in, if you take the span of B and if you take the span of B prime. So these both are spaces. They both are subspace of the vector space V. What they proved is these two are same. They both span the same subspace. You don't get different subspaces. Okay, and that's why this is a very good result. Okay, and that's why people play with orthogonal basis. Okay, so that I have talked in my earlier lecture on motivation to study this process. So make sure you have a look. Okay, so just keep this in mind. It helps you to convert any arbitrary set into orthogonal set. And see, once you have orthogonal set, you can easily have orthonormal set. What is orthonormal set? It is an orthogonal set. Moreover, each vector has length 1. So what you do, you divide each of the vectors v1, v2 up to vn by its length. So therefore, those vectors becomes orthonormal vectors. Okay, so that's why it is also called as orthonormalization. So given a subset, apply Gram Schmidt to get orthogonal set. Once you have orthogonal set, you divide each vector by its length. Length means its norm. Okay, so norm of a vector is defined as square root of inner product. So divide each vector by its length, then whatever the set you get is the orthonormal set. Okay, so now let me try to explain this geometrically, because what I have seen is usually authors, they say this, that it helps you to convert into an orthogonal set and they directly give you the formula. Okay, but let me try to show you this with the help of the geometry. Okay, so it's easy to understand and remember the formula. Okay, so the term that we are going to use here is the projection vector. Now in your junior college, I think you might have seen this formula. Projection of A on B is given by A dot B upon B dot B into the B vector. Okay, you might have seen this in your junior college 11 or 12th. If not, no worries. I'm going to derive this, how this actually comes. Okay, so I'm going to derive this, and this is what we are going to use. Okay, so what is given to us? A set B is given to us, say u1, u2 up to un. This is a subset of the vector space V. I have to construct a orthogonal set. So I have to start with something. So let us start with the first vector as it is. So let us take the first vector as it is. So what is my V1? My V1 is nothing but the U1 itself, because I have to start from somewhere. So let me take the first vector as it is. So my V1 is nothing but U1 is nothing but V1. Now what is my V2? Now if these two are orthogonal, I will take U2 as it is. But if U1 and U2 are not orthogonal, so question is, what is my V2 vector? Let us try to arrive at this. Or actually, let me tell you the formula. The formula that you will see is, from U2 you subtract a vector that is nothing but inner product of upon inner product into multiply by V1, the earlier one. And here what you have, U2 comma V1 upon V1 comma V1. Right, this is the formula that you see. Now let me try to show this geometrically. Okay, so what do you have? You have, suppose you have this as your u1 vector and this is your u2 vector. Obviously you can see the angle is not 90 degree, so these two are not orthogonal. You can see that for u1 something here might be the orthogonal to u1. Okay, so how to construct that? What you do is, you drop this projection, you drop this vector, you project this on u1. So this is my 90 degree. Now what is this vector? So I am projecting here. So now this is a vector, but this vector is lying on u1. That means what? This vector is a multiple of u1, right? Because like for example, if you take this 1 comma 1, if I take any vector on this line, suppose say 2 comma 2, what is that? It is multiple of 1 1. If I take 3 comma 3, it is again a multiple of 1 1. So if I take any vector on 1 comma 1, it is again a multiple of 1 comma 1. Okay, so here if I take any vector on u1 bar, it is a multiple of u1 bar. So what is this vector? This vector is some multiple of u1 bar. What is that multiple? Let's try to find it out. Okay, now here you can see, if I go from here and then I go here, let me call this as say x bar. Now see, this is 90 degree. Question is, what is x bar? Actually this will act as my V2. Okay, so now what do we have? We have alpha dot u1 plus x bar is u2 bar. Okay, now let me take inner product with v1. Now this u1 is nothing but my v1. So let me take inner product with v1. So alpha dot u1 plus x with v1 is equal to inner product of u2 with v1. So on both sides I have taken inner product with v1. Okay, now let me erase this. Now again, by apply the linearity property, I have alpha u1 v1 plus inner product x v1 is equal to inner product u2 v1. But what is the inner product of x with v1? This is my x vector over here and this is my v1. My v1 is same as u1, and we know that this is the orthogonal one. That means the angle is 90 degree. That means this inner product is 0. So what is your alpha? Your alpha is inner product of u2 v1 upon my u1 is nothing but v1. So v1 v1. Right? So what is my x bar? The perpendicular one. So my x bar is nothing but u2 minus alpha u1. And what is alpha? This. So what is alpha? u2 v1 upon v1 v1 dot v1. And this is x bar is a vector which is orthogonal to my u1. Okay, like this is the perpendicular one. So if I draw the parallel one over here, like the parallel vector, so even this is perpendicular to u1. So this is my v2. My u1 is nothing but v1. So now instead of calling this as x bar, I will call this as v2. So this is how your v2 is coming into the picture. You have u1, you have u2, you project here, you get alpha times u1, you take inner product and find alpha, and therefore your x bar, the perpendicular vector which I am calling as v2, is nothing but u2 minus alpha times u1, and this is the formula. So this is how the formula is coming into the picture. Okay, so that was the derivation, and this vector is called as the projection vector. So this is the dot v1. So this is u2 minus this vector is what? This is projection on v1, right? That's the perpendicular line. So this is called as projection of which vector we have projected? u2 on v1. So this is the projection of u2 on v1. We have called v1 as same as u1. So you from u2 you subtract the projection vector, and that is nothing but the v2. Okay, so we got v2. Actually you can check that inner product of v1 v2 is 0. Why inner product of v1 v2 is 0? That means I am saying inner product of this is 0. So what is this? v1. What is my v2? This thing, u2 minus u2 v1 upon inner product v1 dot v1. What is this? By property of inner product, this is inner product of v1 u2 minus, this is a number, so this will come in outside, u2 v1 upon v1 into inner product of v1. This is a number, this is a number, it gets cancelled. Inner product of u2 v1 is same as inner product of v1 u2 by symmetricity, and these two are same, so this goes away. Answer is 0. Okay, so first we found v2 and then we verified that this v2 is actually orthogonal to v1. So good, we had u1 u2, from that u1 u2 we constructed v1 v2 and they are orthogonal. Now how will you construct v3? So for v3, from u3 you subtract something. For v2, from u2 you subtracted a projection vector. For v3, from u3 you subtract a projection vector. Now here a projection vector means a vector u2 was perpendicular to v1. So here your v3 should be perpendicular to v1 and v2. Okay, so I am not going to in that derivation. So here it was some alpha times v1, right? So here alpha times v2 plus beta times v1, because I want a vector which is orthogonal to v1 and v2. That means it is orthogonal to the span. Now the homework for you is you try to find alpha and beta. Okay, it will come out to be, here I have v2, this minus will come inside, and v1. Your alpha will come out to be, here it is v2, so here v2 comma v2, and here it is v1, so here v1 comma v1. Now here u3, so u3 with v2 and u3 with v1. So that's a nice trick to keep this in mind. So now this is a vector v3, you can check inner product of v3 v1 will come out to be 0, inner product of v3 v2 will also come out to be 0. What will be your v4? It will be u4 minus the projection vector, a vector which is orthogonal to v1, v2 and v3. So it will be u4 minus, in the bracket, some alpha v3 plus beta v2 plus gamma v1. Then you find alpha, beta, gamma, the same formula will come into picture. So now you just pause the video and you think, write down v4. If you are not sure, you can check in the book or you can put in the comment section, I will verify for you. So this is the formula that one uses to convert any given set into the orthogonal set. Now let us go for some examples. Okay, now let's start with the simplest one. Let me take v equal to r3. Okay, and here I have u1, u2, u3, these three vectors. You can check that this is not an orthogonal set because I am taking dot product as an inner product on r3. What is the dot product of these two? 1 plus 0 plus 0. Answer is 1. So the dot product is not 0. Therefore, these two are not orthogonal. Similarly, this two and this two, the dot product is non-zero. Therefore, this is not an orthogonal set. I have to convert this into orthogonal set. Okay. So this is my u1. So what do we do? By process, we will find v1, v2, v3. What is my v1? It is same as u1. What is my v2? From u2 you subtract the projection vector. Now here the inner product is dot product, so I take u2 dot v1 upon v1 dot v1 into v1. What is u2? 1 0 1. What is the dot product? 1 plus 0 plus 0 upon, what is the dot product? 1 plus 1 2 into v1 1 1 0. What is this? 1 minus half is half, 0 minus half is minus half, and 1 minus 0 is 1, right? So this is my v1, this is my v2. Is the inner product of v1 v2 0? This is my v1, this is my v2. Let's verify. Half into 1 is half, minus half 0, half minus half 0, half minus half is again 0. So good, my v1 and v2 are orthogonal. Now let us try to find v3. Okay, so what is the formula for v3? From u3 you subtract the vector which is projection to v1 as well as v2. So multiple of v2 and multiple of v1. For v2 you divide by v2 dot v2. For v1 you divide by v1 dot v1. Here u3 with v2 and here u3 with v1. It's good to remember in this way. Okay, now here I will need this. This was 1 1. Okay, what is my u3? u3 is 0 1 1 minus u3 dot v2, u3 dot v2. So 0 minus half and 1. So 1 into minus half is minus half. So this is half only upon v2 dot v2. So 1 by 2 into 1 by 2 is 1 by 4 plus 1 by 4 plus 1 into v2. What is my v2? Half minus half 1, right? Minus u3 dot v1. u3, my v1 is same as u1. So 1 into 0 plus 1 plus 0. So this is 1 upon v1 dot v1 into 1 1 0. Okay, so what I will need is, I will need u1. So let me write down here, u1 was 1 1 0, which is same as v1, right? Okay, what was my v2? My v2 was half minus half and 1. Okay, good. So I have written down v2. So I don't need this. Okay, I don't need even this. Okay, cool. So this is my v3. Now what is this? Let us try to do the calculation. 0 1 1 minus, what is this? 4 5 6. So 1 by 2 upon 6 by 4. So 4 by 6 minus half the third vector. What is this? 2 1s are 2 2s are. So this is my 1 by 3. So what is this? 1 by 3 into this. So 1 by 6 minus 1 by 6, 1 by 3. And this is what? Minus half into 1 1 0. What do you get here is 0 minus 1 by 6. Okay, so let me write down here my v3. 0 minus 1 by 6 minus 1 by 2. 1 plus 1 by 6 minus 1 by 2 and 1 minus 1 by 3. So you simplify this and your v1, v2, v3 will be an orthogonal set. That means these three vectors will be orthogonal. If you want orthonormal set, you divide your v1 by the length of v1. So what is my length of v1? It is square root of inner product of v1 v1. Square root of, this is what? v1 dot product v1. What is this? This is 2. So if you want orthonormal vectors, so instead of 1 1 0, you divide by the length, which is root 2. So it will be 1 by root 2, 1 by root 2 and 0. This will be the first vector, orthonormal if you want. Again do the same thing, you find length of v2, divide by the length. Then you get another orthonormal vector and same for v3. So if you want orthogonal, v1, v2, v3 are the answer. If you want orthonormal set, then you divide each of them by the length. Okay. So I hope this part is clear. The calculation part I am avoiding because I feel you can do that. But if you get stuck, you can ask me in the comment section, not to worry. Let me take the second example. Let me take v to be set of all 2 cross 2 matrices over with real entries. Okay, I'm defining inner product. So if I take any two matrix, the inner product is trace of AB transpose. I have shown earlier that this forms an inner product. Link you can find in the description that this forms an inner product. So here, if I give you B to be say 1 1 0 0, if I take 1 0 1 0 and 1 1 1 0, you call this as X, Y and Z. You can check that you find X into Y transpose, you find the trace, it will come out to be non-zero. You find Y into Z transpose, find its trace, it will be non-zero. So this is not an orthogonal set. I want to find orthogonal set. So I want to find V1. Let me call V1 to be the first vector as it is, or let me call this as U1, U2 and U3. Let me stick to the same notation. So let me call my V1 as U1. What is my V2? It is U2 minus the projection vector. What is that? U2 dot V1 upon V1 dot V1. Sorry, not dot. Here it will be inner product. Inner product dot V1. Right? Now what is this? 1 0 1 0 minus. What is the inner product? It is the trace of U2 into V1 transpose. So U2 into V1 is this. So U2 into this transpose. So actually it is nothing but the dot product. So 1 1s are 1 plus 0 plus 0 plus 0. So this is 1. If you are not sure what I just now I did, you just find U2 transpose, or sorry, U2 into V1 transpose. Find V1 transpose, do U2 into V1 transpose and then find the trace. Your answer will be 1. Okay. V1 dot V1 means V1 into V1 transpose. So V1 into V1 transpose. So 1 into 1 plus 1 into 1, this will be 2. And here into again V1, 1 1 0 0. So when I subtract this, so I have 1 minus half is half, 0 minus half, this is minus half, this is 1, sorry, this is 0 0. Okay, so this is another vector. This is my V2. And now you can check, if you do V1 into V2 transpose, your trace will come out to be 0. Trace of V1 into U2 transpose will come out to be 0, and therefore V1 and V2 are orthogonal. Okay, so I hope you got the idea what I have done. Okay, so actually I have spent much more time on this when I talked about trace of AB transpose forms an inner product. So if you have a doubt in this, you can see that lecture. Okay, but keep one thing in mind. If this is my A, this is my B, A into B transpose, and then taking the trace of that matrix is same as you simply take the dot product and multiply 1 into 1 plus 1 into 0 plus 0 into 1 plus 0 into 0. That will what the trace will come out to be when you do A into B transpose ka trace. Okay, so that's one thing. So and similarly I will not find V3 I will give you as a homework, because I just want to give you the flavor of this. And the last example that I would like to take is of that of polynomial space. Okay, so V is my set of all polynomials of degree at most 2 with coefficient as real numbers. And let me define inner product of P of x comma Q of x as P of minus 1 into Q of minus 1 plus P of 0 into Q of 0 plus P of 1 into Q of 1. Already I have proved that this forms an inner product. Now if I give you B to be 1 x and x square, this is not orthogonal. What is inner product of 1 comma x? 1 of minus 1 is 1 into minus 1 plus this is nothing but 1 only. So 1 into 0 plus P of 1 into Q of 1. P of 1 is 1, Q of 1 is 1. So in this case, yes, they are coming out to be orthogonal. Great. What about x and x square? For P of minus 1 is minus 1, Q of minus 1 is 1. This is 0. This is what? Q of 1 into this is again 1. Okay, cool. So this is also coming out to be 0. What about 1 and x square? Are they orthogonal? Let's try to check. What is p of minus 1? 1. Q of minus 1? 1. P of 0? 1. Q of 0? 0. Plus Q of 1 and P of 1 is again 1. Here the answer is 2. So since these two are not orthogonal, so this is not an orthogonal set. Okay, so one has to find the orthogonal set with respect to this inner product. Okay, so what you do is my B prime, since these two are orthogonal, this will be same only. So if this is my U1, U2 and U3, I want to find V1, V2, V3, right? So my V1 is same as U1. You try to find U2, it will come out to be X. You don't trust me, so let us try to find. What is my V2? It is U2 minus U2 dot U2 V1 upon V1 V1 into V1. What is my U2x minus? What is the inner product of x and 1? Inner product of x and 1 just came out to be 0. That's what we computed, right? Upon inner product of V1 with V1, whatever that number will be, I don't care. But anything into 0 is 0. So this completely goes away. My V2 is x. Okay. And now I want to find V3. So what will be my V3? It will be U3 minus inner product of U3 with V2 upon inner product of V2 V2 with V2 minus inner product of U3 with V1 upon inner product of V1 V1 into V1. Okay, now let's try to find this. So this is x square, P is x square and Q is x. What is P of minus 1? 1. Q of minus 1 is minus 1. So 1 into minus 1. P of 0 is 0, Q of 0 is 0. P of 1 is 1, Q of 1 is 1. Upon inner product of x comma x into x minus. What is inner product of x square and 1? Actually we just computed and it came out to be 2. Inner product of 1 comma 1 is nothing but again 2. You can compute if you want, and here into 1. So this is x square minus 0 minus 1. So therefore your V1 is 1, V2 is x, V3 is x square minus 1. So my B is not the orthogonal set, but my B prime is orthogonal set. Okay, so that's how one can find the orthogonal set using Gram Schmidt process. Now what you do is, after this session, from the book, I hope you have a pen and book with you, just compute the missing parts. Okay, whatever I have not calculated, you do calculate, and once you have orthogonal set, you do compute orthonormal set as well. And what you do is, for the first example, I took dot product as an inner product, right? So for the first one, what you can do is, you can take x bar dot y bar as x1 y1 plus 2x2 y2 plus 3x3 y3. Under usual dot product, this was not there, right? This is not there when we take the standard dot product. But now I am defining this as an inner product. And you will see that the B which I took 1, 1, 0, the first example, with respect to this inner product, you will get a different orthogonal set. So orthogonal set varies as soon as you change the inner product. Okay, so I hope this is clear. If you have any doubt, you can ask me in the comment section. Thank you.